quick little review slash teaching, depending on how much of this stuff you actually remember or learned the first time. But we need to be able to deal with square roots, okay? Rationalize the denominator, simplify our square roots, so forth and so on. So if I have, let's see, let's start with like the square root of 12, okay? So that's not a perfect square. And if I want to simplify it, then I need to, now if you were taught that what you want to look for is the biggest perfect square that divides into the number, that's not wrong, but it's also not the best way to do everything. I would suggest a factor tree. Now I could say, I know factors of 12 is like 2 and 6 or 3 and 4, but if I pick one that has a perfect square in it, that would probably be a better choice. So I know that 3 times 4 is 12. So I got this 4 right here and the 3, right? So in my tree, I'm going to circle every time I get to a prime number, like I can't break that down anymore. I can also stop at a perfect square. I'm going to do one of two things. I could stop here, or depending on where you are in the knowledge base of this, you may want to continue that on to a 2 and a 2, and then you've got prime numbers there. Okay, so then all my branches, that's called prime factorization. 12 is 2 times 2 times 3. Then I look for pairs. I have 2 2s. They come out of the square root as a regular 2. This 3 doesn't have a pair, so he stays underneath. And my answer is 2 square roots of 3. Does that sound familiar? Something you should have done in geometry and in Algebra 2, actually. So let's do, what do you think about the square root of 8? So I know that 8 is 2 times 4, right? So I'm going to circle my prime number. Now, since this is a perfect square, I can stop there, and I can say, all right, well, then that means that I can take the square root of 4, it's 2, and then that square root of 2 stays underneath. 8 is 2 square roots of 2. Okay, we good with that? Do something like that. All right, so what about the square root of 27? What do you think that would be? If I can get 9 times 3, right? I can take the square root of 9, it comes out as 3. That guy stays underneath. 3 square roots of 3. All right. The other thing we have to be able to do with square roots is to be able to rationalize the denominator. So should have done that when you did special right triangles and stuff in geometry, and then again in Algebra 2. But let's say that we solve something, whatever. Our final answer is 2 over the square root of 3. Okay, so that value may be perfectly fine, but we are not allowed to leave irrational numbers or have square roots in the denominator. So we have to do what's called rationalizing the denominator. You can multiply anything in the world by 1 and not change its value, right? And 1 can take on different forms. It could be a 1. 1 could be 3 over 3 or 5 over 5. That's all 1, right? If I want to get rid of the square root of 3 in the denominator and not change the value of this fraction, then I'm going to multiply this by whatever this square root is. I need to multiply it by a square root of 3. And if I multiply by the square root of 3 over the square root of 3, my blue fraction has a value of 1. Do we agree with that? So we multiply straight across. The numerator becomes 2 square roots of 3. Denominator, what's the square root of 3 times the square root of 3? Square root of 3 times the square root of 3 is technically, it's the square root of 3 times 3. So the square root of 9. And what's the square root of 9? 3. Square root of 5 times the square root of 5 is the square root of 25, which is 5. The square root of 10 times the square root of 10 is 10. Over there I have the square root of a monkey times the square root of a monkey is a monkey, because it doesn't matter what it is, right? The square root of a million times the square root of a million is a million. So anytime you multiply two identical square roots like this, you just get what's underneath. Okay, so rationalizing the denominator can kind of happen a lot. So if we have 4 over the square root of 5, then to rationalize the denominator, I would multiply by the square root of 5 over the square root of 5. That gives, these two things just get stuck together. I get 4 square roots of 5 over what? 5. And then you can't cancel those 5s out because they live in two different worlds, right? Does that make sense? We good with that? Okay, so this will come up some more in what we're doing today. So let's talk about irrational zeros. Let me get my drink. So what makes a number in general rational or irrational? A rational number can be represented by a fraction. So it doesn't have to be a whole number. It can be a decimal. So 0.5 is a rational number because I can represent it as 1 over 2. Pi is an irrational number because it goes on forever and doesn't repeat. And I can't, there's not a fraction I can represent it with. Square root of 3, it's an irrational number because there's not a fraction that I can make out of it. Rational being having the root word ratio in it. Okay? All right, so we're going to look at some irrational zeros. Everything we have factored and all the zeros that we have found so far have all been rational. So this says to find all our zeros and write in simplest form. All right, so we've got to factor this. I do not have a GCF. A is not 1, so I'm going to factor by grouping. This is to the 4th power, but that's fine because it's set up like a quadratic. No biggie. So I'm going to multiply 4 times 8. That gives me 32. So then two numbers that multiply to give me 32 and combine to give me negative 33. Negative 1, negative 32. Right? So then I have 0 equals 4x to the 4th. Remember, I figured this out so I can split this term, and that'll give me negative x squared minus 32x squared plus 8. All right, so then I'm going to factor by grouping. So out of these two, I can take out an x squared. That leaves me with 4x squared minus 1. And then a minus 8 leaves me with 4x squared minus 1. So then 0 equals x squared minus 8 times 4x squared minus 1. What questions you got about that? We get all so far on the factoring part of it? Okay, so can I factor this some more? Yes, this is a difference of squares. This one is not, but this one is. So 0 equals, I'm going to leave that x squared minus 8. Then this is going to give me 2x plus 1 times 2x minus 1. Okay, so at this point, I have factored it as much as I can. So now I'm going to find my zeros. And so when I have a bunch of these, I like to do this so I can kind of keep them separated and keep my act together here. So we know when we're trying to get our zeros, we set each little factor. So these are my 3 factors. This is a factor, this is a factor, this is a factor, right? I set each one of them equal to 0. So this would be 2x minus 1 equals 0. So then I add 1 to both sides and get 2x equals 1. X equals a positive 1/2. I am 100% fine with you skipping these 2 steps. If you can look at that and know that it's just 1/2, that's fine. So here I would know I could see this and it's just x equals negative 1/2. Okay, did it on the first one so you know that that's literally what we're doing. So then here, this gives me x squared minus 8 equals 0, which means x squared equals 8. Which means x equals, so in order to get rid of that square, I have to take the square root of both sides, right? When I take the square root of both sides, what do I always have to write? So I don't end up in math jail. What? Plus or minus. Good. Sorry, I was talking over you. Plus or minus, so it's plus or minus the square root of 8. That's not a perfect square, so I need to simplify it, right? The basic ones like square root of 8, square root of 12, square root of 27, after a while, you'll keep doing them and then you'll just kind of know them. They kind of come to you pretty quickly, right? Because this is 4 and 2. So that means that x has to equal plus or minus 2 square roots of 2. So I have these as my zeros, and that's what I'm looking for. So x equals, I have plus or minus 2 square roots of 2. and then I have a positive and negative 1/2. I can separate them. I could also say it's plus or minus 1/2. Either way is fine. Sometimes, especially if you have a long list of them, if you can double them up, it's better, but it's fine either way. What questions do you have? Okay. So really the only difference between this and the factoring and solving we've been doing is that some of them will be irrational numbers. That's pretty much it, okay? So y'all do number 2. I want you to wow me with your factoring skills. I want you to factor that, find all the zeros you can find, and then I'll make sure that we can finish it up correctly. Yep. Yes, it does, yes. Do you understand why they're okay? Before you do that, you're on the right track. You have to have x squared by itself, so divide by 3 before you do that.
Oh, I thought it was...
Yeah, you got to have just the variable when you do that. Okay. If y'all got it at least, okay, y'all all got it factored well. So let me help you with, because this solving does get, I want to make sure you know these steps. But you can factor it. That was the main thing I was concerned with, so we're good there. So let me just get this factored real quick. I'm going to take that 3x squared. That leaves me with x minus 5, negative 4, x minus 5. So then I get 0 equals 3x squared minus 4 times x minus 5. So y'all all stopped there and started to solve, which is good because you can't factor this anymore, right? So I'm going to solve this. This is real easily becomes x equals 5, right? So that's one of them. This, I do have 3x squared minus 4 equals 0. So I'm solving for x. So this would be 3x squared equals 4. So just like solving for x, like even if that was just a plain old x, your next step would be to divide by 3. So we divide and get 4/3, right? So x is equal to plus or minus, here's where you take the square root of both sides, the square root of 4/3, okay? So one other thing maybe I should have said when we were reviewing our square roots at the beginning is that if you have an entire fraction like that underneath the square root, it's the same thing as the square root of 4 over the square root of 3. Like you could write them either way, right? So since I can write it like that, I can take the square root of 4, right? It's going to give me 2, so I get plus or minus 2 over the square root of 3. But then what's wrong with my answer? There's a square root in the denominator. So I multiply this by what? Square root of 3 over the square root of 3. Very good. I multiply straight across, so I get plus or minus 2 square roots of 3 over what? 3. Very good. And then this is my other x. So my zeros in the end, I have plus or minus 2 square roots of 3 over 3 and 5. What questions do you have? We good? Don't make up math with the square roots, okay? Think about what you're doing with them. Ask yourself if it makes sense. Treat them like variables a lot of the times, knowing that you can't, cancel these 3's out or anything weird like that because they're two completely different things. We all good? All right, so let's talk about the fundamental theorem of algebra. Okay. First of all, this talks about a complex zero. Do you remember talking about complex numbers in Algebra 2 by any chance? Remember imaginary numbers? So we're not going to get into the imaginary numbers, but that's the first time you hear complex numbers. So I'm just going to give you a quick rundown of like the complex number system, but we're leaving the imaginary stuff out. If I have, so an imaginary number is a plus or minus b times I, right? So I could have 4 plus 3i. That could be a complex. That could be one of my imaginary numbers, right? So that's considered a complex number. But 4 is also considered a complex number because let's say if a equals 0, so if a equals 0, right, a plus bi, then I would have 0 plus 3i, which is just 3i. Like there's your imaginary number, right? Or if b equals 0, then I would have 4 plus 0i, which is just 4. So all of the real numbers that we talk about and that you've known like forever, those are also complex numbers. Imaginary numbers live in the complex number system. I think sometimes there's some confusion and you think that complex numbers have to be imaginary, and they're not. They just live in that system because the first time you ever heard the term complex numbers is when you started talking about imaginary numbers. Okay, so real numbers are imaginary numbers. All three of these are complex numbers, but these two are actually imaginary and that one's real. But they all are in this form right here. Okay, so that's just kind of a little FYI because it talks about it in this little factorization theorem. It says if C is a complex zero, okay, so let's say 3 is one of our zeros. It's a complex zero. So that doesn't mean it has to be imaginary, just a number. It's a complex zero of a polynomial function, then x minus c is a linear factor of the polynomial. So on the front, we factored some, but then we stopped because we're like, oh, we can't factor anymore. We're actually going to get everything completely 100% factored. So this means that all polynomial functions can be completely factored. Okay, so we're going to find the zeros, just like we did on the front. Then we're going to completely factor it. So we're just adding that little piece on there. And I was going to change this, and I didn't, so I need to give you a different function than that. Otherwise, we get imaginary, and I was trying to avoid that. We're going to use 9x to the 4th minus 73x squared plus 8. That's our function. All right, so we need to factor it. It's a 4th degree, but it's a trinomial set up like a quadratic, so we're going to be okay. So I take 9 times 8, that gives me 72. Two numbers that multiply to give me a positive 72 combine to give me a negative 73. That's pretty easy, right? -1 and negative 73. So then I get 0 equals 9x to the 4th minus x squared minus 70. Oh, what am I doing? It should be 72, not 73. I'm a dork. Okay, 72. That should be really easy, but I still mess it up, just like I said. Minus 72x squared plus 8. I realized that when I was thinking, that's not going to factor out. All right, so then I factor by grouping here. I can take out my x squared. Leaves me with 9x squared minus 1. Then I can factor out a negative 8. That leaves me with 9x squared minus 1. So I get x squared minus 8 times 9x squared minus 1. So that x squared minus 8, I can't factor it anymore. 9x squared minus 1, can I factor that another time? Yep, that's a difference of squares. So I get 0 equals x squared minus 8 times 3x plus 1 times 3x minus 1. Then I can find my zeros. So this would be x equals a positive 1/3, x equals a negative 1/3. Then this would be x squared equals 8, which means x equals plus or minus the square root of 8, which is, what's the square root of 8 simplified? 2 and 2. 2 square root of 2. Very good. Okay. So it says to find all the zeros. So we just found those. So our zeros are plus or minus 2 square root of 2 and plus or minus 1/3. The second part says to find the complete factorization. So we factored as much as we could at this step, but it's not completely factored because this can technically be factored some more, and we know what these are. If I gave you a list of zeros, because that's a little different there. Let's say that I gave you, say our zeros are -1, 2, and 4. Then that would tell me that I know that I have factors in there. Since that's a -1, I'd have an x plus 1, I'd have an x minus 2, and I'd have an x minus 4. Does that make sense? Because that's where they come from. So then that means that when I actually factor this, that first one, I can actually use these and I get x plus 2 square roots of 2 times x minus 2 square roots of 2. But then I have to be careful because I am not doing x plus 1/3 and x minus 1/3. Because if I look at what I had, when I multiply my x's together, I have to have a 9 up there. So notice how this 1/3 came from the 3x minus 1. You always have whole numbers in there, or irrational numbers, but they're not fractions. So this one I can see where it's coming from. It's coming from right here. But like if I didn't have this to look at and they gave me this, kind of like I did here, we just had to come up with it. If you think about the fact that we get it from x equals 1/3, right? So instead of just subtracting it over, I got to get rid of the fraction. So I'm going to multiply through by 3. So I get 3x equals 1. Then I subtract and I get 3x minus 1 equals 0. So be careful with the fractions in there. And make sure you put it back like it looked before. So we have 3x plus 1 and 3x minus 1. So then this is completely factored. This is where we could get it to by the factoring that we know, and then this is what we can get it to after we know the zeros. See the differences there? It's very minor, but it's there. All right, what questions you got? All right, you do number 2. See how far you can get on that one, and I'll make sure we all get it. Okay, you're here. So try the little factor tree thing. 2 numbers that multiply to give you 12. Okay, and then 6 can become what? So you have 2 of these. That comes out as a regular 2. And then square root of 3. And don't forget your plus or minus. You got it. So I got plus or minus 2 square roots of 3. You had that, right? Okay. And then negative 3. So there are the zeros. That was the first thing it asked for. Then the complete factorization, like we just need to pretty much fix that because we already had that part in there. So that's going to be x plus 2 square roots of 3 and x minus 2 square roots of 3. And then this is a negative 3, so this is not x minus 3, it's x plus 3, right? So make sure you don't mess that up. I mean, yes, you have this to look at, but if you are just given a set of numbers, make sure you're getting them put in right. Okay? What questions you got? Easy enough? More factoring. We're going to be factoring like crazy for a lot of stuff we're doing, so keep pushing forward. If you're struggling with it, practice a little bit more on it. Maybe practice a little bit on some roots. Would that help you if I gave you something to kind of practice on? Okay, awesome.